Today we're going to talk about the grid. We're going to talk about how we move, buy, and sell electricity. And this is one of several lectures that we have about electricity. So electricity, it's not an energy resource, right? It's a energy currency. So there are conversions involved, right, with how we transmit this electricity. We're going to talk about that today. But we really have 3 different lectures focused on electricity. We've got the one today where we talk about how you move, buy, and balance electricity. Diana is going to talk about how we generate electricity and what the economics of electricity are. And then we've got Zach Ming coming in, a former TA of this class who now works at an energy and electricity consulting firm and teaches a class in the winter about electricity economics. And he's going to talk about how we transition to a fully renewable energy and clean energy electricity grid. We also have a lecture on energy storage, which is definitely relevant to electricity, as we'll talk a little bit more about today, but is also relevant and cross-cutting to other topics in this class, including renewable energy and transportation. We're going to show a video to give you some context on how we manage our electricity grid.
It's 7 p.m. and in homes up and down the country, cookers, heaters, television sets are being switched on. At the National Grid Control Centre, National Balancing Engineer Simon Jeffcoat's on duty. Arrayed on the wall in front of him is his view of Britain from above. The country's been tipped on its side, and every high-power electricity connection from the far north of Scotland to Cornwall has been mapped out in loving detail. But Simon is bracing himself for the most difficult moment of his day by watching EastEnders. When the credits start to roll, he's going to have to deal with a massive surge in electrical demand, what's known as a TV pickup.
We're expecting a pickup of around about 3 gigawatts, which is 3,000 million watts, or equivalent to 1.5 to 1.75 million kettles going on. So we expect the demand to pick up over a period of about 5 minutes.
Power surges like this are unique to Britain. No other country in the world switches on so many kettles in so short a time. To cope with the strain, Simon has had to put specialised power stations on standby as far away as Snowdonia and Scotland. These hydroelectric plants can set thousands of tons of water plunging down the hillside at a moment's notice, generating huge bursts of power in a matter of seconds. But Simon is also having to ask our neighbours across the channel for a favour.
To assist us with the end of EastEnders, we have the French link picking up, and they are picking up 600 megawatts at 100 megawatts a minute. So that's, again, a very rapid response.
Simon is slave to this flickering frequency indicator, which he has to keep as close as possible to 50 hertz. If there's not enough power in the national grid, it drops off the scale. Too much, and it shoots off the other side. And he has to judge his timing perfectly, even if the BBC isn't quite working to schedule.
We've been notified of a time for the end of the programme, and it hasn't actually finished at that time.
Which means?
Simon fires off instructions from his keyboard. On the other side of the country, vast turbines rumble into life.
Dinorwic is up to 150. I've just instructed them up to 300 megawatts now. Festiniog is up to 90 megawatts. It's full output. French piling in now.
2 minutes into the TV pickup, and it looks like there's going to be more than enough power to go round. And then suddenly there's a problem.
What is it? Oh, is it the French link?
There's a trip on the additional supply from France.
Locations
The frequency has dropped dramatically.
Going to be fine, I'm sure.
Simon has just moments to cover the sudden shortfall. He rapidly sends out instructions to get one more hydroelectric plant online. Then, once more, the supply heads back into the safe zone.
It was an immediate decision. As soon as the frequency dropped through 49.8, I had to react.
The delicate balance of our electricity supply has been restored, for now. And across the country, 1 million kettles keep on boiling. Britain's day is drawing to a close. By now, all that can be seen of Britain from above is illuminated by the power that Simon and his colleagues are squirting round the country. 8 million streetlights have flared into life.
The video is somewhat old, and we'll talk today about how advances in technology and data sensing and other kind of so-called smart technologies have brought smart technologies to the grid and helped to automate some of this. But at the end of the day, you still need people there to make sure that if something goes wrong, like the French link doesn't come online, something needs to happen. So even if you go to the California ISO today, you'll see elements of what Simon is doing play out in real time. We talk a lot in this class about supply side, right? And how we generate energy and how we generate electricity. But the demand side matters just as much, right? And not just understanding when demand is going to peak so that you can make sure that there's enough supply to meet that, but also understanding demand as a resource itself, right? Because you can, invest in more efficient tea kettles in order to bring that spike down. Or you could ask a bunch of the population to boil tea at a different time, although that might be really hard in England. So there's a lot of tools that electricity grid operators have available to them to manage supply and demand and manage even the integration of more renewable energy resources onto the grid, as we'll talk about today. All right, so we'll dive into a lot of the concepts from this video today, including how importing electricity from neighboring regions, in this case, if the French link went down, where did he get electricity from? Somewhere else. He got electricity from somewhere else, another country, and how that can help with resiliency and reliability. We'll also talk about frequency and how managing frequency is important, all these great concepts. Let's have a discussion about how this complex system that is the power grid has evolved over time. Historically and traditionally, the electricity grid has operated in the way that you see here in this diagram, right? You've got big centralized power plants transmitting electricity over long distances in one direction to the ultimate end users, the residential, commercial, and industrial customers. But how is that changing? What changes are we seeing in our electricity grid? Yeah, huge growth in data center demand. And we'll talk more about that too, but an interesting dynamic there is oftentimes we see centralization of data centers in one place, where like a data center might use a similar amount of electricity as an industrial facility, but you typically don't have as many industrial facilities concentrated in such a small surface area. So it's not only huge growth in electricity demand from data centers and AI, but also in particular areas, which creates strain on the grid in that particular region. We've definitely got increasing renewable energy, right? That has different load profile, has different generation profiles than, say, a traditional coal or natural gas or nuclear-fired power plant. For a long time in the US, we actually had fairly flat electricity demand, but recently we've seen increases from sources like data centers. Yeah, electric vehicles, huge source of demand. All right, and we'll dive into some of these trends today, but we've also seen growing deregulation resulting in increased competition in our electricity sector. We'll talk about that. We've seen energy storage become a much more economically viable tool for balancing the grid with declines in battery costs and manufacturing scale. Which really creates this new tool that helps with renewable energy integration, but also just generally enabling grid operators to meet supply and demand in real time. All right. So we're seeing a lot of changes happening in our electricity grid that can make it more challenging, but also in some instances easier for grid operators to keep the lights on. Another big trend or change influencing the electricity grid is climate change. So as we talked about in the climate change class, we've seen with climate change a huge increase in weather-related disasters, everything from wildfires to severe storms. And by and large, power outages are caused by weather events. You got tree-related, but typically that means that because of extreme weather, like strong winds related to storms, trees are coming into contact with power lines and causing outages. And this is one of the reasons why we see a lot of utilities investing significantly in hardening the grid, including with support from federal funds. Things like managing foliage around transmission and distribution lines or undergrounding wires. So just to give a few examples, we were talking about Puerto Rico earlier of some really significant blackouts in our history. We've got in 2017, Hurricane Maria wiped out about 80% of Puerto Rico's grid in what was one of the longest blackouts in history. About 675,000 people were without power and it took 9 months for the grid operator to fully restore power to the island. Some of you may remember we've also got some significant wildfire events that occurred in the 2017 to 2021 timeframe that were started by power lines and really helped by climate change. Those dry, high wind days that were increased because of temperature increases as a result of climate change. So many of these wildfires that we saw were caused by those power lines coming into contact with transmission lines. And because of that, it became relatively common for California utilities and utilities across the West to preemptively and proactively shut off power during high wind, dry days to avoid these wildfire events. We've also got the 2021 Texas power outage. You guys had a recommended reading, I believe, about this, where in February of 2021, an unprecedented icy winter storm hit Texas that led to the forced power outage of about 4.5 million customers over the course of multiple days. And because it was so cold and you had a storm going on, there were many deaths involved, almost 100 deaths, and lack of access to food and safe drinking water. From your readings, what was the cause of the power outage? So Texas has its own electricity grid and it allows it to avoid certain regulation at the federal level, but it also means that it can't import electricity from neighboring states or from, say, Mexico as well. And because of that, they weren't able to import electricity to avoid that supply-demand imbalance that led to the power outage. Also, if the power outage hadn't happened, it would have been really an unprecedented peak demand moment for the electricity grid. So there's not a lot of demand side management happening, efficiency or demand reduction efforts. Another big contributor to this is about half of the Texas grid's generation capacity was offline and unavailable because there was a lack of winterization of the natural gas power plants and pipelines. So, immediately after the power outage, a lot of conservative media outlets were blaming the fact that Texas is such a leader in wind and increasingly solar that the power outage happened. But in fact, it was because the natural gas power plants were not online. All right. Okay, and more recently, we've got power outages caused by, for example, Hurricane Milton, and just on the heels of Hurricane Helene in Florida, as another example of significant weather-related power outages. All right, so we talked about weather-related power outages and strain on the grid, but in addition to that, another change that the grid is experiencing is an significant increase in wind and solar generation, not just in the US, but around the world. And this is paired with an acceleration of coal and nuclear power plant retirements that are not only old, but also increasingly uneconomic. So this chart is showing our historical power generation mix from Bloomberg New Energy Finance and forecast under their economic transition scenario. So pretty significant curves there. In California, the challenge of integrating more and more solar into the electricity grid are depicted by the so-called duck curve that you learned about from your readings and videos. To recap, the shape of the duck refers to the shape of the net demand curve or net load curve. Load is another term for demand. So the net load curve here is the green curve, and it's the total electricity system demand, which is the blue one on top, minus renewable energy generation. The net load curve captures the need for non-renewable energy generation capacity to ramp up and down as wind and solar vary on the grid. So wind and solar, because they have no fuel costs, they have no marginal costs, they get dispatched first, right? So that's why you've got this net load curve. So the ramping need of non-solar and wind generation capacity is particularly somewhat high in the morning when you've got the sun coming up and lots of solar capacity coming on the grid, and a little bit of a peak in demand. But it's particularly high in the evening in that kind of 5 to 7 p.m. period where you've got 16 gigawatts of net load need, right? Where your natural gas, your nuclear, your coal power plants have to ramp up in order to meet this need, right as the sun sets and people come home and turn on their air conditioning, particularly in the summer. And they also are increasingly plugging in their electric vehicles to get them charged. Yeah, 16 gigawatts in 3 hours out of a total demand of about 25 gigawatts, which is pretty significant, right? And it's not easily accomplished with your coal and nuclear power plants. They don't ramp up and down very easily, right? You probably learned about that in your nuclear lecture. Nuclear plants, they probably take about a day or two to turn on and off, and coal-fired power plants, hours. These are the so-called baseload power plants. So growing renewable energy is increasing ramping needs. And the other challenge that comes up with this duck curve is, as you get more and more solar on the grid in the middle of the day, you might have a negative net load curve. Where you have more solar generation than you have demand for that generation. And there are a couple things that you can do with that excess generation. You could curtail it, which means turning it off, which is not something you really want to do because it's a valuable resource. You could store it if you had batteries, for example. You could also incent sources of demand to shift to the middle of the day. When you have this cheap and available electricity resource. But we'll talk more about these types of tools that grid operators have to integrate more and more renewable energy resources onto the grid. There's the duck curve, in case you didn't see it before. And you can see the duck curve live on the California ISO website in real time. But this is another view from a recent NREL National Renewable Energy Laboratory study that shows the role of solar in that duck curve. So the different colors here in this chart relate to different electricity resources. And you can see the main load curve, which is the solid line at the top there. And then the net load curve is here. And you can see that ramping need is increasingly met. This was on a really peak demand, the highest peak demand day in California last summer, because last summer was a really hot summer across the US. And you can see that solar is kind of helping to reduce peak demand for a part of the peak demand period. But when the sun sets, that's really when a lot of ramping requirements happen. And energy storage is increasingly helping to meet that ramping need. California is definitely a leader in solar energy integration, but as more and more other regions and states adopt solar, they're starting to see the duck curve as well. It's not quite as pronounced as in California, but this is an example that you can see from ERCOT, which is the Electric Reliability Council of Texas. It's the Texas electricity grid, where you see similar curves there. So as we talked about, it's not just the supply mix that's changing on the grid. Demand is also changing. And you've got air conditioners that are a big source of new demand. Air conditioners typically make up about a third of peak demand on the grid. So huge driver of when peak demand occurs on the grid, as we talked about. If you have a hot summer day, the air conditioning demand is going to cause the highest peak of the year. And of course, with rising temperatures and climate change, that's also causing more and more electricity demand for air conditioning and more peaky electricity demand. We've got a similar story for electrification of transportation and buildings causing higher electricity demand, both of which have the potential to also increase peak demand on the grid and exacerbate those ramping requirements. To give us a sense of scale, a typical US home has a peak demand of about 8 kilowatts, and a typical EV level 2 charger draws about 7 kilowatts. The level 2 charger is what you want if you don't want to take 24 hours to charge your car. So adoption of an electric vehicle, if it coincides with the peak demand period of your home, could pretty much double that peak demand of your home. So pretty significant. And the magnitude of the impact of EV adoption or building electrification or electrification of industry on electricity demand and when peak happens is going to depend on both how efficient that electrification is, but also when it happens and how effective we are at managing when demand occurs, like telling when EV owners should charge their cars, for example. Right? We want them increasingly to charge their cars in the middle of the day. All right, and as we talked about earlier, the increase in data centers and increase in demand for AI is resulting in significant increases in electricity demand. And the magnitude of that increase is going to depend on how efficient those chips and those data centers are. We've seen an increase in efficiency, a decrease in energy intensity of AI and data center technologies. But by and large, demand for those technologies has outstripped those efficiency increases, resulting in a doubling of electricity demand from data centers in the US. All right, so these evolving grid dynamics, I hope they give you a sense that the value that the grid is providing is not just in the electricity generated, but also in the reliable delivery of that electricity through the transmission and distribution system to your homes and businesses. So you can see here for a typical PG&E bill, the Pacific Gas and Electric, which is Northern California's main public utility, that electricity generation only makes up less than half of the electricity bill. A big portion is attributable to distribution and transmission. So we'll talk about these value dynamics and how we value electricity, because it's not just the cost per megawatt hour that we care about. I also want to make a quick note here. We're going to talk about the difference between wholesale electricity and retail electricity. When we talk about wholesale electricity, that's the cost that a utility pays to generate electricity. Retail electricity is what an ultimate end user pays on their utility bill. So it includes all these other costs related to distribution and transmission. It's like the difference between, what a grocery store pays for their food versus what you pay the grocery store, if that makes sense. All right, so what is electricity? It's the flow of charged particles or electrons. And as we talked about, electricity it's not a resource, right? It doesn't occur naturally in our environment, at least in any useful form. It's an energy currency. There are a few different ways that we can generate electricity. The typical and traditional way is from a heat engine using energy resources to boil water to generate steam. You can also harness kinetic energy from certain energy resources directly or through electrochemical processes. But the result across all of these is the same, right? You generate electricity. And the primary way that we generate electricity today and for the last century has been through thermoelectric processes, that top way. And that process has largely been dominated by fossil fuels, your coal and natural gas power plants, and to a lesser extent nuclear. But we're seeing that change today with the growth of solar and wind on the grid. All right, so these are some of the ways that we characterize electricity and the ways that we measure. So you learned in your first class about the difference between power and energy using the analogy of water flowing through a pipe. Energy is measured, in the case of electricity, in watt hours or kilowatt hours, and it's analogous to the amount of water flowing through your pipe. And power, which is measured in watts or kilowatts, is analogous to the flow rate of your water. So to give a concrete example, a microwave draws about a kilowatt of power at any given time when it's turned on. So if you take some popcorn, put it in the microwave it for an hour, then it's drawn a kilowatt hour of electricity. But you probably also have some pretty burnt popcorn, so you're probably not going to do that. All right, and just to give you a sense of economics, the cost of a kilowatt hour of electricity is about 15 cents on average in the US, which is pretty cheap, right? So there are 3 important properties of electricity. Hopefully you read about this in the math module number 5. You've got current, which is measured in amps, which refers to the rate at which electrons flow through a given point or area. Electrons are charge. And you get a current to flow through a conductor like a wire by applying a voltage to it. So voltage measured in volts is analogous to the pressure in difference in your water pipes. And then resistance, again using the water pipe analogy, is analogous to the friction in your pipes. And resistance is measured in ohms, OHMS. All right, this chart, it gives you a sense of the scale of consumption and demand in terms of power. So that's the watts or kilowatts. So charging your cell phone is about a watt. We talked about how a microwave draws about a kilowatt. The average home demand, we talked about peak demand being about 8 kilowatts, but the average home demand is between 1 and 1.5 kilowatts. And in terms of supply resources with power plants, this can really range quite a bit. Everything from a 5 kilowatt solar system on your roof to a gigawatt scale nuclear or coal-fired power plant. All right, so let's talk about how electricity is transmitted. Okay, so an important concept in understanding how we transmit electricity is the difference between alternating current and direct current. which is two types of electricity. So AC, it has oscillating current and voltage, and DC has constant current and voltage. Generators by default generate AC because when you have a coil rotating within a magnetic field, with every 180-degree rotation of that coil, you've got a change in current and voltage. PV panels or batteries, for example, they've got fixed positive and negative terminals, so they have constant current and voltage. So the US grid predominantly runs on alternating current, or AC, and the speed with which the current alternates is called frequency, and that's measured in hertz. So the US grid needs to operate within a very small band, around 60 hertz, or 60 cycles per second. So every generator on the grid needs to be operating roughly at 60 hertz. And you saw in England, that was 50 hertz, so it varies slightly by country. So our grid is dominated by AC power, but that wasn't always a given. And the origins date back to the War of the Currents in the late 19th century, when Thomas Edison, his vision for the electricity grid was one dominated by DC. He imagined that the grid would be made up of small-scale power plants operating within a very limited region, and serving those local customers within that region. And this contrasted with the vision of George Westinghouse and Nikola Tesla. Tesla, like Edison, was an inventor, and he invented the AC motor and the transformer. And unlike Edison, Tesla and Westinghouse, they believed that the grid should operate on alternating current, or AC, and be made up of large-scale power plants that transmit electricity to customers over huge regions. With AC, at least at the time, it was a lot easier to step the voltage up and down, and if you want to transmit electricity over long distances, stepping up that voltage is important to reducing losses. Again, that was covered in the math review sheet number 5. And so AC is important if you want to have large-scale power plants transmitting electricity over large areas to different customers. Why do we want that? What's the benefit versus like small distributed power plants serving a few different customers in a smaller region? Yeah, so you got economies of scale when you can build bigger power plants. The cost per watt of building a larger utility scale solar plant is significantly lower than the cost per watt of building a rooftop solar project. We'll dig into that in the solar lecture. But also it increases resiliency because you diversify both sources of supply and sources of demand, right? So to give a simple analogy of the importance of that diversity, if, let's say, you and I are neighbors and I'm a night owl, you're a morning bird, and I use most of my electricity at night, you use most of your electricity during the day, it wouldn't make sense for both of us to have 5 kilowatt generating systems, right? Instead, we could share a 5 kilowatt generating system and get the same services. So in that same way, different generation resources are going to have different generation profiles that help better meet demand as it varies throughout the day, and create redundancies as well, like it would be in the case of Texas if they were able to import power during the big Texas power freeze in 2021. But similarly, different end users have different demand profiles as well. So bigger grids help with balancing supply and demand. Yeah, so ultimately, because of that, AC won because at the time we could step up voltage of AC easier that allowed us to transmit it over long distances to different customers. So our transmission and distribution system is designed for AC power. Typically, you've got your centralized power plant generating AC power if it's an AC generator at 3 to 30 kilovolts. Kilo is 1,000. So kilovolts is 1,000 volts. Before it goes into the transmission system, you've got transmission substation that's with a step-up transformer that steps up the voltage of that electricity and increases the voltage to at least 138 kilovolts, but it could be as much as 1,000 kilovolts. Before it reaches your local grid, known as a distribution system, it goes through a distribution substation with a step-down transformer that steps down the voltage to 4 kV to 13 kV. And then before it gets to your house, it's stepped down again to 120 to 240 volts. Electricity consumption is measured through a meter, which is why we've got the terms behind the meter or in front of the meter. Behind the meter refers to anything on the customer side of the meter, and in front of the meter refers to anything on the utility side of the meter. So your house, it runs on alternating current. What comes out of the plug is AC. And some of your appliances use AC, some of them actually use DC. So your big white appliances that have motors use AC, like refrigerators and washing machines. But things like your phone, your laptop that run on batteries, they're typically running on DC. So your plug often has, or your laptop often has, a rectifier, which converts alternating current to DC, and also has a transformer to make sure it gets it to the right level of voltage from the building's 120 volt socket. If you want to convert DC to AC, like if you have a solar panel on your roof, then you need what's called an inverter. All right, so we got a few different props. We've got a bare aluminum wire, and then we've got some insulated transmission lines and distribution lines as well. You got a copper one and I think an aluminum one as well here.
Yeah.
The insulated ones are heavy, so careful. Okay, so while those are getting passed around, we'll talk about how the US is really made up of 3 main grids. You've got the Western interconnection, the Eastern interconnection, both of which have cover parts of Canada, and then you've got Texas. So as we talked about, Texas has its own electricity grid. It limits interstate electricity transfers that allows it to avoid certain regulations by the federal government, which is why they couldn't import as much electricity during the Texas power freeze. So the flow of electricity is restricted between each of these 3 grids. So even though they all operate on the same average frequency of 60 hertz, the individual interconnections aren't in sync with each other. And so they can't be directly connected through AC interconnections. So there are only limited connections between these different grids where they're connected by high voltage direct current lines, HVDC lines, that use a rectifier to convert the AC to DC, transmit them to the next grid, and then an inverter to convert them back into AC in the right phase. Within each of these grids, electricity travels the path of least resistance. So you can think of these grids as like a big pool where there's limited ability by grid operators to control where electricity flows. So because of this, it means that there's a difference between the physical flow of electricity and the contractual flow of electricity. For example, Stanford has a power purchase agreement with multiple power plants in Central and Southern California. Even though they don't necessarily know whether or not they're getting the physical delivery of that electricity to campus, because they contracted for those plants to be built, the solar power plants, they can claim that electricity. And, of course, there's a lot of discussion around ensuring, the importance of ensuring that the profile of generation that an entity is contracting with meets their profile of demand. But generally, conceptually, it's important to understand that physical flow, we have limited control over unless you have like an island-in grid. But contractual flow really is what determines who's getting what electricity. So even though AC won out in the War of the Currents, DC is still fairly prominent in our electricity system, both in terms of our end uses, but also rising in terms of transmission lines. because since the Edison days, we've seen advances in solid-state inverters and voltage source converters, which make it easier to step voltage of DC up and down. And today, actually, those high voltage direct current lines, HVDC lines, actually have lower line losses than their AC counterparts. But the problem is that they have higher losses in the conversion, the transformation of the electricity, the conversion of the electricity from AC to DC and then DC to AC back again. So those HVDC lines, we only really see them over long distances where the efficiency gains are great enough over those longer distances to offset those losses in converting from AC to DC. And a great application for those HVDC lines is taking large sources of supply, like wind energy in the Midwest, to areas of demand. Because, you know, while the Midwest might have a lot of wind energy, they don't necessarily have enough load centers to consume that electricity. So we're seeing a lot of efforts to build long distance HVDC lines to take that wind to centers of demand elsewhere. But big challenges with interstate transmission lines and you know, permitting with folks that don't necessarily want those transmission lines sited in their backyard. All right, let's talk about how the electricity industry is structured. So a utility is an entity that maintains infrastructure that delivers essential goods to you, to the public, whether that's electricity, natural gas, water, historically the internet. In this map, it shows all the different electric utilities that serve California. There are at least 50 of them. Historically, electric utilities have been regulated as what are called natural monopolies. And a natural monopoly exists in a particular market where if one firm can serve a market at a lower cost than multiple firms serving that market. Often natural monopolies have economies of scale and high fixed costs. This photo demonstrates why natural monopolies exist, right? It's a photo of New York City in 1888 with a bunch of different telegraph and power lines strung over the city. So it's more costly and inefficient to have multiple utilities serving the same customer. So because of this, typically the government will grant natural monopolies or a single utility a regulated monopoly status to be the single utility to operate transmission and deliver electricity in a region. But the challenge with having a regulated monopoly is that entity, that utility, can charge any cost that they want to an end customer, right? Because the customer doesn't have any choice for which company to buy electricity from. So in exchange for the government granting regulated monopoly status to a utility, the government regulates the price of electricity. So regulating rates is a really important reason why the electricity industry is so regulated. There are a few other reasons why we regulate, like safety and reliability, environmental impacts, but today we're largely going to focus on price regulation. There are two main entities that regulate electricity in the US. You've got the Federal Energy Regulatory Commission at the federal level that regulates interstate wholesale electricity generation and flows. And then at the state level, you've got public utilities commissions, those PUCs that regulate public utilities on the and what customers ultimately get charged, those retail electricity rates. So historically in the US, the utility landscape looked a little bit like this, right? With hundreds of vertically integrated monopolistic utilities, each operating power plants and transmission and distribution in their own utility service territories. And there was limited competition or sharing of generation resources between those utilities. So this diagram here, it shows the different assets that a utility might own. You've got the wholesale generation, transmission and distribution, and then the retail customers. So historically, everything that was in the dotted square was considered a natural monopoly. And as a result, we had those vertically integrated utilities. But over time, what we've realized is that wholesale generation actually isn't a natural monopoly. It's really the transmission and distribution systems that are that natural monopoly. So recognizing this over time, we've seen deregulation in wholesale generation and introduction of competition there in a process that's known as wholesale deregulation or restructuring. So that refers to the shift from the vertically integrated utilities to multiple companies competing and providing electricity generation beyond just the utility, and open access to the transmission and distribution system. So the first step in this deregulation process actually happened during the OPEC oil embargoes in the 1970s that I talked about in the History of Fossil Fuels video that I think you had assigned earlier this quarter, where the US federal government, in an effort to diversify our energy mix, passed the Public Utilities Regulatory Policies Act. That's a mouthful, PURPA, which required electric utilities to purchase electricity from third-party independent power producers, or IPPs. Prior to PURPA, if you were a utility and you owned a coal-fired power plant, or if you're talking about the 1970s, maybe you also owned an oil-fired power plant, you had no incentive to buy electricity from another source, right? Because you wanted to maximize your asset that you had. But with PURPA, it really played a big role in opening up the electricity system to other generators, particularly initially natural gas generation, and later on to renewable energy generators as well. So PURPA was a big step in electricity deregulation, and over time we've seen increased efforts to advance that deregulation, including with FERC Orders 888 and 889 in the late 1990s that established nonprofit entities to operate the grid and ensure open access to the transmission and distribution system. These nonprofits are called ISOs and RTOs, independent system operators and regional transmission organizations, that operate open competitive processes for power producers, those independent power producers, to sell electricity into wholesale markets and use the transmission and distribution system. So while the transmission and distribution system is still owned by typically those utilities, utilities are required to make their systems available to other IPPs. And the RTOs and ISOs are the ones that make sure of that. So today we've got 7 RTOs and ISOs across the US that serve about 2/3 of load, of demand in the nation. This means that in these regions, in the RTO and ISO regions, wholesale electricity prices are no longer determined by regulation, but they're determined by open and competitive wholesale electricity markets. And the implications of that have been pretty significant, right? Both in terms of reliability and in terms of renewable energy integration. Because as we talked about earlier, when you have a bigger and bigger grid, sharing electricity generation resources and diversifying those demand sources, you've got increased reliability. And it also means that, that coal-fired power plant or that nuclear power plant has to now compete directly with renewable energy generation resources, which have zero marginal cost. So I'd say today we're seeing coal and nuclear power plant retirements pretty much everywhere, but early on, a lot of the early retirements happened primarily in these RTO and ISO regions where you have that wholesale competition, where the traditional generation resources couldn't compete with the lower cost renewable electricity resources. All right, so we talked about wholesale competition. Let's talk about retail competition. So in wholesale competition, like you see here, you've got competition at the generation level, right? But the utility still has the direct relationship with the retail customer. But some states have also pushed for retail competition, where multiple generators, multiple utilities can sell directly to retail customers, and retail customers can choose who they want. If you live in Texas or Australia, you are in a retail deregulated region, and you can choose which utility you purchase your customer from, or your electricity from. So in the US, I believe about 13 states and Washington, D.C. have full retail deregulation in those orange colored states up there. But the open competition on the retail side, it also means that the retail price of electricity is no longer regulated, right, by the Public Utilities Commissions, which can introduce challenges and significant risks for ultimate end users, like in Texas, where customers experience really high prices on a regular basis during those periods of supply-demand imbalance, like during the Texas power freeze. Several states have experienced challenges with retail deregulation, including California, that attempted to embark on a process towards retail deregulation in the early 2000s. And the result is that several companies, Enron in particular, attempted to manipulate retail electricity prices by tripping purposefully generation sources offline, causing electricity prices to spike, and also resulting in rolling brownouts and blackouts. And also the first bankruptcy of Pacific Gas and Electric. So that really put a stop to retail deregulation in California, which is why you see that we only have partial retail choice in California, where a limited number of commercial and industrial customers are granted the opportunity to purchase electricity directly. Stanford was one of those. We're what's called a direct access customer. So because of the challenges involved in retail deregulation, many would argue that the benefits of retail deregulation don't outweigh the risks and the costs, which is why we don't necessarily see a lot of traditional retail deregulation advancing in the US. But we do see retail choice advancing in other ways. For example, through the increases in distributed generation with people putting solar on their roofs, or through large commercial and industrial customers procuring electricity directly by entering into contracts directly with renewable energy resources and renewable energy generators, like Stanford with our solar power plants in Central California. All right, so let's talk about the different entities involved in the electricity sector. The different types of utilities. So you've got investor-owned utilities that are private, like Pacific Gas and Electric, PG&E. These are regulated by the Public Utilities Commissions. You've got publicly owned utilities like the City of Palo Alto Utilities, CPAU, or the Sacramento Municipal Utilities District, SMUD, that are both owned and managed and regulated by their respective local governments. You've also got some limited federally owned utilities like Tennessee Valley Authority, TVA. TVA is the only one that has retail customers, but these federally owned utilities, they're typically created for purposes other than electricity generation. TVA, for example, was created to promote the economic development of the Tennessee Valley after the Great Depression. Another federally owned utility that isn't a retail utility, Bonneville Power Authority in the Northwest, was created to market and sell the hydropower generation that was built in the Northwest in order to support the world wars. And finally, you've got power marketers that are financial players. They don't necessarily own electricity generation themselves. They just buy and sell power in order to take advantage of price arbitrage opportunities. So Enron was a power marketer. All right, so this shows the breakdown of players of utilities on the retail side, and this shows the breakdown of different players on the wholesale side. You've got investor-owned utilities that own generation. You've also got independent power producers and those government-owned utilities and cooperatives. And you can imagine that prior to PURPA, independent power producers were a significantly smaller portion of this pie chart. So let's talk about how we maintain reliability on the grid. So as you saw from the video earlier, the tea time video with Simon, grid operators, they really have to strike this delicate balance between supply and demand, meeting supply and demand in real time, and having to maintain frequency and voltage within a certain range. And when they fail in this endeavor, we've got blackouts. In the US, we have a federally created entity, the North American Reliability Corporation, or NERC, that is meant to create reliability standards and enforce them for the electricity grid in North America. And NERC created what are called balancing authorities, that are the entities that implement reliability standards and are responsible for meeting reliability requirements on the ground. So if you're in an ISO or RTO region, then your ISO or RTO is the balancing authority. If not, it's your utility. So RTOs and ISOs, not only do they manage those open, competitive wholesale electricity markets, they are also responsible for ensuring supply and demand are being met in real time and enforcing reliability requirements. All right, we talked a little bit about the smart grid earlier. As we discussed, with the advent of or with advances in data sensing and other technologies, that has created benefits for the grid. A lot of people might conflate a smarter grid with a more distributed grid that has more, say, solar on rooftops, but that's not necessarily the case. And in fact, if it's not managed correctly, could create reliability challenges. But really, when we talk about the smart grid, we're talking about things like smart meters, right? Where over the past several decades, we've seen this transition from analog meters at the home to smart meters, where with an analog meter, you used to need to have meter readers from the utility company come out to your house once a month to read your meter to understand how much demand how much electricity you've used, and as a result, charge you on your utility bill. But with smart meters, that's automatic, where smart meters send, sub 15-minute data to the utility on a regular basis, which is also really important to understanding blackouts, right? Before smart meters, a utility would just have to wait to get phone calls from different parts of the grid to triangulate where a blackout was happening. But now with smart meters, they know who isn't getting power. So smart meters is a great example of that. Another example would be synchrophasers, which are mailbox-size devices that are placed throughout the grid that measure frequency and voltage pretty much in real time, so that grid operators can understand the health of the grid. All right, so that's a quick primer on reliability. Let's talk about how we buy and sell electricity in those wholesale power markets. A useful way to think about electricity project costs is called levelized cost of energy, or LCOE, which takes the lifetime costs of an energy project, including fuel costs, operations and maintenance, and initial capital expenditures, or CapEx, divided by the lifetime production of that electricity generation resource. So it really helps give a sense of the true cost of generating a megawatt of electricity. And this is something that, by the end of this class, you're going to know how to calculate LCOE of a power plant. So this is an LCOE assessment from Lazard, which is a large asset management firm. They release it every year. And you can see that different electricity generation resources have different costs per megawatt hour, right? But LCOE is not the whole picture, right? It just shows costs, not necessarily the value of those electricity generation resources. And we can better understand the value by understanding how electricity markets work. So let's think about what some of the different value factors are. We care not just about whether or not a megawatt hour exists, but how quickly that megawatt hour can be generated. In other words, how quickly can your power plant ramp up and down? Particularly with the duck curve and increasing renewable energy resources and peak year demand, like we talked about earlier, what we care about is not necessarily whether a resource is always on, like a nuclear power plant. We care about whether or not it can ramp up and down quickly in response to those quick changes in demand. It's also about how reliable those megawatt hours are, right? If I call on a power plant to power up, like the French link in Simon's video, is it going to be available? You've also got factors like fuel price risk and variability, and also predictability. right? Even though a solar project isn't always online, we generally know when the sun is going to rise and when the sun is going to set, right? And then we also care about the social and environmental costs of these different resources. And of course, there are markets as well, like carbon markets, that help value the social cost of different resources. So because there are these different characteristics beyond just cost per megawatt hour, we have different markets in the US that value these different characteristics and put a price on things like rampability. And this summarizes those different markets. Within competitive wholesale electricity markets, which are again present in those 7 RTOs and ISOs in the US, you've got 3 main types of markets segmented based on time scales. So you've got the ancillary services markets that compensate generators for how quickly they can come online. And they're largely meant to ensure reliability on the grid. You've got the energy markets where generators bid in day ahead, hour ahead, 5 and 15-minute increments typically. And then you've got your long-term planning and procurement processes where utilities and other entities enter into long-term contracts with generators that ensure enough supply is available to meet demand, even on the highest peak demand days. So we'll talk about each of these 3 markets in turn. Wholesale energy markets are where the bulk of electricity trading happens, and it's the biggest determinant of wholesale electricity prices. We talked about the fact that there are day-ahead and 15-minute markets. These are the so-called real-time markets. And hopefully it gives you a sense that the more frequent your trading is, that trading happens in a market, the more a grid operator has the ability to ensure there's sufficient supply available to meet demand. And you can imagine that only generators that can ramp up and down quickly can operate in those real-time markets, right? So if you're a coal-fired power plant or a nuclear-fired power plant that takes hours or days to ramp up and down and turn on and off, you're not going to be operating in these real-time markets or in the ancillary services markets. And this is a really important concept, right? Because you hear a lot of myths that you need more coal and nuclear for a more reliable grid. But in fact, reliability increasingly means flexibility. And coal and nuclear power plants, those baseload power plants, don't provide that flexibility. Okay, so how this market works, and this is an example from Texas. You can go online in this resource from the Weber Group and play around with this tool. But how the market works is each generator bids into a market, typically priced at their marginal cost. So in this graphical representation of a bid, of a hypothetical bid, you've got capacity on the x-axis, where each line represents a generator bid, and the color represents the resource. So orange is coal, for example, blue is natural gas. And then the y-axis is the bid price for each of those generators. So each generator bids in, and where demand falls on that particular day, in this case it was about 60 megawatts, that's the price, that's the market clearing price that all generators get for that particular time frame. In this case, it was $41.42 a megawatt hour. So even though wind and solar bid in at 0 because they have 0 marginal cost, right? You don't have to pay the wind to blow or the sun to shine. They're getting $41.42 a megawatt hour. This is behind the meter. So this is a wholesale price. This is a wholesale market example. So $41.42 a megawatt hour. You would then add the transmission and distribution costs and all that to get to what is ultimately charged to a customer on their utility bill. Yeah. So occasionally we see this market clearing price go negative, and there are a couple different reasons for that. First is that some renewable energy projects get a subsidy in the form of a dollar per megawatt hour. So a wind project might get the production tax credit, which is a federal tax credit at $23 a megawatt hour. They might also get a renewable energy certificate. We'll talk more about that in the Intro to Renewables lecture. So they can bid in at a negative price and still break even. But the other reason why costs might go negative is if you have coal and nuclear power plants operating in this market and they don't want to power down, it's costly for them to power down, they're going to bid in at a negative price as well to make sure that they get in the market and get under that market clearing price. Hopefully this gives you a sense that wholesale power prices, they vary over time. You can see huge variability in the Texas market here in summer of 2019, but also by location. This is an example of Texas, again, in September 2019, where you see a lot of negative pricing in West Texas because you have a lot of wind energy supply there, but not a lot of demand. And limited transmission capacity to transmit that supply to the demand centers in the Houston and Dallas-Fort Worth areas. But you see high pricing in those areas, right? Because you have a lot of demand, but not enough supply. So there is a locational value to energy as well as a time value of energy. You've got long-term capacity markets where utilities and other entities are going to enter into long-term contracts with a generator just to ensure that there's enough capacity in the event of peak demand. So they might say, hey, generator, I want you to be available for 15 days out of the year when I anticipate significant peak demand, and I'm going to pay you just to be available, even if you don't need to come online. So that's capacity markets. In California, we don't have formal capacity markets, but we have what are called resource adequacy markets, where all utilities need to have, I believe, at least 15% a capacity available for 15% above forecasted demand. And then you've got ancillary services markets that pay a premium for assets depending on how quickly they can ramp up and down in response to short-term variability on the order of subseconds. So hopefully this gives you a sense that grid operators have a lot of tools available to them for balancing the grid and integrating more and more renewable energy resources, including electricity market design. Because that market design varies by ISO and RTO region. Integrating more and more flexible resources like energy storage and natural gas, and expanding electricity grids like regional integration, expansion of ISOs and RTOs. Nevada, for example, isn't a part of an ISO or RTO right now, but they are working towards combining with an ISO or RTO like CAISO. And others that you'll talk about with Diana and with Zach Ming, like investing more in demand-side management and trying to control when people charge their electric vehicles. So because of this, we've seen huge amounts of renewable energy resources integrated into the grid. And we're seeing that happen at increasing rates. All right, thank you, everyone.